Okay. Okay, so just a quick overview. I'm going to provide a brief overview of the generational heap and generational task, which is a collection task. A little bit of historical background. I want to introduce Scavenger, which is the current implementation of GenCon for OpenJ9, because I'm going to be comparing the Evacuator performance versus Scavenger a bit later on. And we're going to present the Evacuator algorithm in some detail, and I'll give you some highlights of some early results with what I call the base model Evacuator, which I'm presenting here. Okay, so the generational heap, probably all know this, but I'll just cover it in any case. Generational heap is just a range of RAM, 1 gigabyte, 4 gigabytes, up to 64 gigabytes, or actually 62 gigabytes for the generational GenCon policy in OpenJ9. It's divided into two spaces. There's an old space and a nursery space. New objects are always allocated in the nursery space. And the generational hypothesis, what makes this all work, is that most objects die young. So we're going to allocate most of our objects in the nursery space and dispense of them in the nursery space as well. If objects survive long enough, they are considered persistent, and persistent objects move into and get copied into tenure space. Now, there's a basic operation that copies, that does the copy. It's called copy forward. That's kind of cool. It's an atomic operation. So when a thread is going to copy an object, it'll reserve some memory for the object, so we've got the memory all laid out. And then it'll go and try to do an atomic operation to flag the object as having been copied, and if successful, it gets to copy the operation, or copy the object. That does two things. Removes cycles from the graph, from the reference graph, and it prevents two threads from copying the same object. So only every object that gets evacuated from evacuation space is evacuated exactly once. It also needs to be scanned exactly once. What I mean by scan is you to instantiate an object scanner which knows how to navigate the object and find the reference fields within the object. Every reference field asks, are you in the evacuation space? If it is, that needs to be copied. So this is a recursive process. You start with the root set, copy the roots, scan each one of the roots, copy their dependents, and continue until every object in evacuation space has been copied and scanned, and then you're done. So the way that the mutator works here, or the application works, so it will start allocating from a space that's been reserved in the nursery space, and it will allocate until that space is full, and then some thread will try to allocate an object and fail, and that will trigger generational collection. Generational collection starts out, they were evacuating this stuff. Young objects is copied into some spaces that was reserved. This is empty space initially when the TC starts. You start copying young objects into the survivor space, and old objects are copied into the tenure space. When this space has been completely evacuated, all of the young live objects are now concentrated in here, and all of the old objects that were in the live objects are in the evacuated space and copied to tenure space. This is now empty. You slide this boundary over a bit, because this is all empty space, and reserve some more of the next survivor space over here, and this becomes your next allocation space. And that's the whole generational cycle. I'm going to introduce some artifacts that I'll be talking about throughout the course, throughout the presentation, that are important for the generational collectors. When you're copying an object, you don't reserve or allocate just enough space to copy that object. That would be ridiculous, and people put a lot of pressure on the memory subsystem. So each thread will allocate a large chunk of memory to copy objects into. I'm calling that white space. Typically, you'll allocate 128 kilobytes of white space, and you start filling it up. Copy objects into it sequentially, back to back, until the space is almost complete. In order to do that, you need to have a copy head. You need to know where to copy. So that's where copy space comes in. The copy space is a white space with a copy head. So you just copy, 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 as I said, until you get close to the end of this thing. And when you get close to the end, we're going to have a remainder at the end eventually, where you don't have enough space to copy some object in. And we don't want to throw away large chunks of reserved white space at the end of these things. So we have a threshold, 768 bytes. That's our limit. Okay, anything like if we have less than 768 bytes of white space left, we can throw that. We can truncate that the copy space at that point, and then you get a workspace. Workspace has a base pointer, an end pointer, and it's full back-to-back and contiguous objects. What I've just described, copying sequentially into a copy space, that's called breadth first copying. And basic vanilla generational copier or generational collector, that's how it will work. It will fill up these copy spaces breadth first, throw them into a work list, and then come back and start doing the same thing, copying, scanning these guys, and copying into another copy space breadth first, and so on and so on. So another twist on this, I'll show where this came from in a minute, is a scan space. A scan space is a copy space with a scan pointer. Instead of copying breadth first, you can just copy an object into some white space, okay, and then start scanning it immediately, and copying its children just ahead of the scan pointer in the same space. When you do that, let's say you copy a string object into an empty white space, start scanning it. The string has one child pointer, points to a car array. So if you start scanning that immediately, hit that car, you get pointed to the car array, you're going to copy it right next to the string, so they're co-located. Right? So this is something that one of the main objectives of what I'm trying to do with the Evacuator and what we tried to do in previous editions of Scavenger is we try to do that as often as possible. The idea being that you get the copy, you get the referring pointer, and the head of the referent object co-located within the same cache line. Cache line, if you look at a modern processor, you've got on board on the processor, you've got a large memory bank with 64K on a 64 processor, 32 kilobytes of instruction cache, 32 kilobytes of data cache, and memory moves from main RAM into level 1 cache in 64-byte chunks. 64-byte chunk is a cache line. We're trying to increase cache line containment. That's one of the main things we're main objective to. And we achieve that by copying within the same, scanning and copying within the same scan space. So white space, copy space, workspace, scan space, main artifacts that we're using in the generational collector. So parallel scavenger, as I said, that's our current implementation for the generational collector in OpenJ9. And it's been around since about 2002. Been around for a long time, about 16 years. And the original collector was just a basic collector, copy everything breadth first. Roots, copy them breadth first. Fill up workspaces as you go. Copy the workspaces onto a work list. When you finish root scanning, go to the work list, grab a workspace, start scanning it, copy breadth first, etc., until you're done. That's just the basic first implementation of the J9 generational collector scavenger. 2005, a couple of researchers, David Sigwart and Martin Herzl, came up with this ingenious algorithm that really is ingenious. They introduced the scan space. Copy and scan within the same scan space to improve object locality. Okay, there are a couple of problems with that, in that if you're thinking about it, picture a scan space, your scan head is moving much more slowly than your copy head. And soon the distance between the scan head and the copy head is going to become so great that there's just no possibility of object locality anymore. Okay, so you've got to do something about that. What do? What they did, said, okay, we've got two scan spaces. We've got one for survivor, and we've got one for tenure. Let's track, always scan the scan space that has the shortest scan copy distance. And we'll switch between them as necessary to always, so we're always scanning within the sky with the minimal scan copy distance. And that works pretty well, except sometimes you don't have the tenure scan space to work to play off against. So your survivors in the scan space won't just grow, the scan copy distance will just grow indefinitely up to 128 kilobytes. So that's not so great. And even if you do have a tenure scan space and the survivor scan space to play off against each other, what if both of their scan copy distances are too great to achieve any kind of object locality? That happens as well. So I thought we could maybe do a little bit better. How can we do that? Key is to limit the size of the scan space. Okay. How do you do that? Limit the size of limit the maximum distance between the scan head and the copy head, and try to get always try to maintain the active data you're scanning and copying within the same cache line, and keep it all in the level 1 data cache. I also saw an opportunity to basically to refactor Scavenger as a monolithic class. It has a thread pool. They said there'll be one GC thread per core. And when a GC, a nursery collection, starts off, these threads are fired up, and these have a run method. And what the run method does, it goes and calls a method inside this monolithic scavenger class. And there was one result of that is that it's kind of hard to see the trees for the forest. If we refactored the algorithm that these GC threads run, refactor that out into its own class, to give us some focus and some clarity, and also just leave what's remaining in the scavenger class. As a collector, it handles whole heap concerns, single-threaded, so it's an opportunity to refactor this. And also, I saw an opportunity to streamline the core collection algorithm, because it's actually pretty simple if you think about it. What the evacuator or scavenger sees as it's copying and scanning, or as it's scanning, it's just seeing slot being a location that contains a pointer into the heap, and it's just going to see slot. And for each slot, it's going to ask, are you pointing into evacuation space? If you are you young, are you old? Copy it appropriately into survivor or tenure space. Very simple algorithm at bottom. So I thought we could streamline that a little bit. I tried to do some streamlining. So we've got a thread pool, and we have an object pool. Each evacuator instance is, we have a pool of evacuator instances. And when the GC thread starts up, there's a controller that binds the thread to an evacuator instance, activates the evacuator instance, and away it goes and does its task. So how do we improve cache line containment, and how do we limit the size of the scan space? Well, we use a stack of scan spaces. Each frame is a scan space, and it's bounded. Here's one frame boundary at the beginning, base of the scan space. And the other frame boundary is 4 kilobytes away from the base. And the rule is that you can copy within the scan space until your copy head touches or passes the frame boundary. After that, you can't copy anymore. Okay, so at that point, what do you do between for the slots between the scan head and the copy head? Well, you have to push them up the stack. So I'll just run through this scenario that I've got pictured here. I've got 3 frames of the stack. Here's the bottom frame down here. I've also pictured an outside copy space, so it's going to receive stuff that we can't copy inside the stack. So to start out with, we've copied a root object, say, and the root object that we have copied is an array, and it's a big array. So a 6K, say, it's bigger than 4 kilobytes. So in order to copy it into the bottom frame, first of all, we allocated a chunk of white space, 128 kilobytes. and we attached it to the bottom frame. Okay, then we copied the array into it, okay? And then we set the stack pointer to the bottom frame, and we start scanning within the bottom frame. That's the first slot. It's an evacuation space. It needs to go into tenure space. So what do? We clip the remaining white space. We've got about 122 kilobytes of white space here. Clip it off, pull it up into the next frame. Now we can copy the object from referred to from this first slot. Copy it up into the next frame, and then push the stack pointer. Start scanning within this frame. Okay. Now we've got lots of white space here still. So scan this first slot, and its call sign needs to go to tenure, so we copy it right beside the parent object. Now we've got cache line containment. This is copy as this reference arc. Here is entirely contained within this cache line. So we've got cache line containment for that copy. Okay, next slot. It needs to go to tenure as well. Copy it right beside the copy head. And we're done with that object. Next object, scan it. Oh, this is a sleep object. It's a car array or something. It has no reference slots in it at all, so we just smoothly scan it over it. Start scanning this guy. It's a null pointer. Skip that. Scan this guy. So it needs to go to survivor space. We're scanning tenure space. Also, it's a large object. I'm constraining the size of objects that you can copy inside the stack to less than 256 bytes. Okay, anything bigger than 256 bytes, that's copied into an outside copy space. And that's the situation here. It needs to be copied into the survivor outside copy space. The next slot needs to go to tenure space, but we've crossed the frame boundary here, so we can't copy inside anymore. Same thing, put the remaining white space off, install it into the next frame, and then copy the object up. Now we still have cache line contained here because this endpoint is contiguous with the base of this next frame. So we still have cache line containment in this case as well. So we're scanning this frame now, top of the stack. When we dispense with this guy, we're done. We'll pop down this guy, finish him up, pop down at the bottom frame. Now, next slide, do the same thing all over again. So we've made 5 copies. We've got 5 copies here. 1, 2, 3, 4, and 5. And 2 of them have cache line containment. 2 out of 5 has 40% cache line containment. So just some of the key features in Evacuator. The scan stack is bounded. You have 32 frames. Once you get up to the top, you have to start copying. Can't push anymore, so you have to copy things outside, everything, small, large, whatever. Copy everything outside until you finish that frame and pop, and then push again. As long as you're on the top frame, you have to push everything outside. Frames are 4 kilobytes wide, and only objects less than or equal to 256 bytes can be copied inside. And you can interleave tenure and survivor frames as required. Outside copy spaces, as I said, each Evacuator thread has 2, one for survivor, one for tenure. They receive objects that are greater than 256 bytes. They also receive objects flushed from the stack, and when we overflow the stack beyond 32 frames. Also, if there's another Evacuator thread that is stalled, okay, running Evacuators will try to provide him with some work for him to do. And the way that they do that is they lower their stack limit so that the stack has only 1 frame, the bottom frame, so that everything has to be copied outside. And as you're copying material outside, okay, you're copying into an outside copy space. It's got 128 kilobytes of white space that you're burning down. And as you're copying, okay, we have a threshold, a work release threshold, which is in installing context, is set to a minimum of 4 kilobytes. Okay. So as soon as you've copied 4 kilobytes into your outside copy space, you can snip that work off as a workspace and put it on your work list, and then it's available for the stall thread to pick up. We have white lists. There's a white list for survivor. There's a white list for tenure. Whitelist is basically a priority queue or a heap, as in heap sort. It can contain up to 15 fragments, white space fragments, and it always presents the largest fragment on top. So we keep all of these remainder fragments that we trim off of copy spaces at the end. Typically, they're less than 768 bytes. They can be larger in some cases, but they always go on a whitelist. And they're burned down or they're consumed by the stack. You need white space for a stack frame. Always go to the whitelist first. Take whatever's there. If it can contain the object you're trying to copy, take it, install it on the stack, copy. Even if it's 760 or 600 bytes, you still got your copying small objects less than 36. You've got a few. You can always burn these guys down pretty quickly. So that helps us to manage fragmentation. And in fact, Evacuator and Scavenger also does a very good job of fragmentation. It's typically less than 1%. And Evacuator does a little bit better with that because it has these white lists to manage these fragments. Finally, we have a distributed work queue. Each Evacuator has its own work list, and there's a distribution bus, and that's called the Evacuator instances. And we have a load leveling protocol so that typically, in general, most of the time, each Evacuator tends to have the same volume of work on its work lists. Okay, so here's a complicated diagram. I'm just using this to highlight these features that I just described, and I want to animate some of the workflow for an Evacuator thread. So each Evacuator thread has all of these features. Here's the scan stack here. It's a whitelist for survivor, whitelist for tenure, copy space for survivor, copy space for tenure. I've got a large objects copy space here as well. So where that comes in is this, when you have a remainder on your survivor copy space, say it's greater than 760 bytes, 68 bytes, and a large object comes along that won't fit in your remainder, well, you're not going to trim that copy space at that point. You're going to allocate just enough memory in survivor or tenure space, as the case may be. Allocate just enough memory to contain that object, copy the object into it, and then just take it as a workspace, throw it onto the work list. So this large object copy space is effectively always empty. It's just waiting to receive. These are large objects and dispose of them onto the work list. Okay, so just to animate this a little bit, say we're scanning roots. You've got a root object, you need to copy it, so you want to copy it onto the stack, regardless of how big it is. It's root object, array, string, whatever. You're going to allocate a chunk of white space, 128 bytes, kilobytes, and attach to the bottom of the stack, copy the root object into it, and then set your scan pointer to the bottom of the bottom frame and start scanning immediately. And as before, just spin that object out, and basically every object that's reachable from that object is going to get copied onto the stack, into the outside copy spaces until everything's scanned and the stack pops. At that point, you do the next root, same thing. As you're scanning roots, you're going to be filling up these copy spaces, outside copy spaces as well, because you'll encounter some large objects. They'll have to be copied they can't be copied into the scan stack. Copy them into outside copy spaces. As they fill up, while we're scanning roots, we set the work release threshold to 4K so that we can get some work onto our work lists in case one of the Evacuator threads has a very small stack and doesn't have a whole lot of work to do. There'll be some work available for him. So after root scanning is complete, Evacuator will turn to his work list and say, okay, I've got some work on the work list, pull a workspace on into the bottom stack frame and start scanning that. And while we're doing that, again, we're throwing some outside work into the outside copy spaces, and trimming, and we, during this phase, we've got a lot of work to do, so we'll increase the work release threshold somewhat, so we get bigger workspaces on the work list. And we just continue to do this until we've scanned that workspace, everything inside that workspace, and pop the stack is empty. At that point, we need to go to the other side copy spaces. If there's any work inside in these outside copy spaces, we'll pull that work into the bottom of the stack, scan it out, and basically you need to clear both of these outside copy spaces before you can go to your work list. You go to your work list, and it's dry, you don't have anything to do, the work list is empty. At that point, well, you've got to go to other evacuators, okay? So at that point, the evacuator would go to there's a controller, has a mutex that controls the distribution bus, take that mutex, so it's got exclusive access to the distribution bus, and go around to all the other evacuators and ask each one, what is the volume of work on your work list? And it'll find the evacuator that has the greatest volume, and it will try to take its work list mutex. Try to take it. Okay, if it gets it, it will ask it, okay, now that I have your mutex, do you have anything in your work list? If it has one workspace in its work list, it will take it. If it has more than one, it will continue to take pull work from the donor's work list into its own work list until they have roughly the same amount of work. If it can't get the first evacuator's mutex because it's busy, then no problem. It's not going to stall or wait for it. It's just going to go on to the next evacuator on the bus and try him. And because we're constantly pulling and trying to level up whenever we get a chance to. That tends to level out the volumes of work on the bus. So if you can't get into the first guy, try the next guy. You probably do almost as well. So you continue in this manner until all of the threads, or all of the evacuator threads, none of them have any work in their work list, and they're all going to stall. They're all going to try to take this mutex and wait for work, but the controller is going to realize, okay, when the last evacuator instance stalls and tries to take this mutex, there's no work. Everybody is stalled. Nobody has anything in the work list, so we're all done. We're finished the collection. So in terms of benchmarking evacuator versus scavenger, I selected 3 different workloads to do this. Now I've been developing the evacuator in iterations, and at what I'm on the base model is the 4th iteration. So I've been running these same workloads. I run 5, each workload 5 times with scavenger, each workload 5 times with evacuator. In total, that's about 10 hours of runtime to do one 5x5 trial with all 3 of these guys. There's a transactional workload. It runs for about 75 minutes for each run. It's got lots of scalar objects, lots of small arrays, 10, 15, 20 elements in them. And it doesn't tenure very much, less than 1% of its evacuation volume gets tenured. Almost all of its objects are small, less than 256 bytes in size. That's the transaction workload. The data compilation workload is actually XML. It's validating XML documents. It runs for about 5 minutes. It's got lots of linked structures in it, linked lists, trees, that sort of thing. It doesn't tenure very much either, and about 75% of these objects are small. Small being capable of being copied inside stack things. This database processing workload, it involves an in-memory database, and it runs for about 5 minutes. It's got lots of arrays of intermediate length, 100 a few hundred elements. Those are the spines of query results or batch updates, that sort of thing. And about 50% of those objects are small. So very different workloads, very different and different percentages of small objects, different kinds of data structures for representing collections of objects. So, and a reasonable representation of what the sorts of things are found in applications. I run them on the same machine every time. It's an 8-core physical x86 64 server. It's running Red Hat Linux. And when we're running, this machine's reserved for exclusive use, and there are no other user processes running for the duration of the benchmarks. I've aggregated, because I've got 3 previous iterations, I've aggregated 20 runs for each workload with Scavenger, and the results in about percent. So just 5 runs for each workload with the Evacuator. So, in terms of cache line containment, how do we do? Well, with the transactional workload, Scavenger gets about 7% cache line containment. And Evacuator is 17%. The data compilation workload, 3% for Evacuator, 13% for 3% for Scavenger, 13% for Evacuator. And with the database workload, 14 for Scavenger, 21 for Evacuator. So we get a fairly substantial bump with for cache line containment with Evacuator. I'm not really very impressed with these results, and I know that we can get better. I've been experimenting with depth first traversal, and if you do depth first traversal with these workloads, you're seeing greater than 40% cache line containment for each one of these guys. And on PowerPC with 128K or 128 byte cache lines, on Z machines with 256 byte cache lines, it goes up even higher. So we're actually getting some benefit here in terms of cache line containment. Evacuation throughput. How much material can you evacuate from evacuation space into survivor and tenure in a given amount of time? For the transactional workload, this is about an 18% improvement in evacuation throughput with Evacuator. For the data compilation workload, that's about 19% better throughput with Evacuator. The database workload is less, it's about 3%. Both Scavenger and Evacuator struggle with this workload because at steady state, after it's taken its in-memory database through the nursery, flipped through the nursery 14 times and finally dropped it into tenure and goes down to steady state, the size of the live sets that are presented in each generational collection are tiny. They're like 7 or 800 kilobytes, and you've got 8 threads competing to evacuate this stuff. So the thread's stalling in both cases. So in those terms, you can see it here. We're stalling about 25% of the time in both cases, Evacuator, Scavenger. For the other 2 workloads, and for well-tuned workloads, you'll typically get for Scavenger or for Evacuator better than 95% CPU utilization. Scavenger does a really good job with this, and Evacuator manages it keeps up with it. So this is the really important stuff. How does this all impact the GC and the application? So there are 2 metrics here. One is reduction in GC time. How much time are we spending in the GC each workload? Like applications see the garbage collector as a necessary evil. They'd like to see these garbage collection times to be 0. Actually starting to get there with Causeless GC, by the way. But for Evacuator versus Scavenger, with Evacuator we've reduced GC time in this workload, transaction workload, by about 13%. Okay. And for data compilation, we're up to almost 15% reduction in GC time. With the database workload, that's a little less, it's approaching 2% reduction in GC time. That's the stall. So that's not too bad. And how does the application like it? How do these workloads like it? Well, the transactional workload, each one of these workloads produces a score at the end of the run, one number. And that's its representation of how well it did in terms of throughput. So scavenger versus evacuator, how do these scores measure up? For the transactional workload, the application throughput is increased by almost 5% with the evacuator. The data compilation workload, we're getting almost 4%. There's better throughput with the evacuator. And with the database workload, it's about 1%. So these are real effects, real benefits to the running application in terms of reducing time in GC and giving more time to the application to run so that it gets more work done. So just to sum all of that up, I don't have enough data, enough numbers. There's a lot of variance in these scores, these application throughput scores. So I don't really have enough data to really do a really good analysis of how these various factors contribute to mutator throughput. But I tend to think that increased cache line containment, basically it's the GC that benefits mostly from that. Get better cache line containment. The GC hits, every time it gets this effect, it basically it skips a read. You're reading and writing inside the same cache line, so you don't have to go and fetch the destination address into level 1 cache. So that accumulates over hundreds of thousands of copy operations, and you get better GC throughput certainly from that. So increased GC throughput reduces the time spent in GC, and I think that the reduced time spent in GC is what's contributing mainly to the boost that we're seeing in application throughput. That's pretty much the end of it. I have some time. Do I have any time left?
I think you're a little bit over already.
I am. Okay. Yeah. Well, I'll just open it for questions.
So when you talk about cache line containment, you just take a look at if the child is close to the parent.
Mathematically, you take the address of the referring pointer and the address of the referred to object, exclusive or, it's also less than 64, yes.
So would it be interesting to take a look at whether that child, you don't have any idea if the child is hot or cold, right?
Of course, I was hoping to do that.
Interesting idea to see that it doesn't really help much.
No.
I mean, I'm putting something negative here. If you have a cold child
unfortunately,
there and the hot child in the next cache line.
Unfortunately, the GC, the evacuator scavenger too,
of course,
doesn't have any clue.
Yeah.
Now, if the JET could give us a hint, and that there are some artifacts inside the ROM class, as a field called instance hot fields. But for this purpose, it's in the wrong place, right? And it contains this wrong information. If in the parent object could identify this is my hottest field, right? Then tweak the object scanner so that we return that slot first.
Yep.
Copy that hot field always right next to the parent object, and then I think we get a significant boost in application performance. Cache line containment would contribute much more to application performance than it does without that information.
That's essentially what Tees, I don't know.
Pardon me?
Tees had done this. One of the students, to see put the hot children close to the or the hot fields actually of
I thought that what she was doing was she was actually reordering
Splitting,
fields.
yeah,
And that's another thing that would help. If you could put if we could locate the hottest field, not only identify, but locate it near the end of the object.
Yeah.
That would be better.
So I guess, if I understand it correctly, what you're doing is you're still scanning objects in the same order, but the way you're doing scanning copying, you're having better cache line containment in the GC. But you're not changing anything with respect to the application's cache situation. Because ultimately you end up with the objects in the same order.
Well,
Technique versus what was here before.
well, the application sees. Well, I mean, the objects are what the objects are, and they either have cache line containment or not. But what happens, I think, is that, and this is why I don't think that it contributes a whole lot to application performance, is that in the nursery, okay, objects die young. And when objects die, you know, the endpoints of a reference are either end of the reference point dies, the reference is gone. So they're very transient in the nursery, and and if you, for where you get cache line containment in tenured objects, well, you don't know whether they're hot or cold. It's hit or miss.
Yeah, so where I was going, what I was going to ask was essentially, if it's changing how you're scanning, right, where the end result is that your objects get shuffled around, so you're trying to optimize your cache containment for the application, and how do you think those two would compare?
Well, I'm not sure how you would, what the difference would be. I mean, when you're copying in the collector, you copy them that they are, and then when you finish the collector, that's what the application sees. I don't see the application doing anything to improve its own cache. So I'm not sure that I understand.
The application would still go for the same objects in the same order, because that's the application's distribution, right? But I guess the thing is if you change the scan order, then you essentially are changing where the objects are placed, right? Which then changes when the application is running its cache.
Sure.
I guess in general terms, what you did was you improved the containment in the PC. I guess how would ops, or how do you think it would compare with having really bad cache containment in the GC by scanning in a more crazy bad way, but getting better cache containment in the application?
Well, so kind of struggling with this. Like, we're comparing here, cache line containment would be a scavenger's algorithm, which doesn't give you very good cache containment, not as good. And you see the application scores improve slightly. I still think that doesn't, because GC is